Well, I appreciate the invitation, and I regret not being able to come. It would have been a wonderful time to see people. So let me tell you what I'm going to talk about. And of course, I'll talk about it. But the purpose of this talk is to describe to you the stationary measure for something called the open KPZ equation, and then to give you some ideas about its construction. And it's in the construction that I hope there'll be some similar objects to things that you study, things like Askew-Wilson polynomials, or really Askew-Wilson processes, a special variant. And I won't go into much detail on it, but I hope I'll whet your appetite. The KPZ equation, which will kind of be the focus of the first part of the talk at least, is a subject that's been really of intense study in the last 35 years due to its value as a random growth model, its remarkable connections with integrable systems, and its ubiquitous occurrence across all sorts of seemingly unrelated problems in mathematics and physics. Now, the open KPZ equation is supposed to model interface growth between two walls, so with two boundaries, and in contact with these boundaries. Equivalently, if you take the derivative of this, it defines a model for stochastic transport between two reservoirs. And so for these purposes, people have been interested in a long time in studying its stationary measure, basically its long time behavior. What happens if you run it for a long time? What does it look like? And that's what we will describe to you. That's the result that we have proved, is we've constructed the stationary measure. And remarkably, it's actually related to a variant of Brownian motion. In particular, Brownian motion is subject to reweighting in terms of exponential functionals. And this is an object that in its own right has been of quite a lot of study in probability in the last few decades. So having told you what I'm going to be focusing on, let me spend the first 5 minutes talking about something completely different. Okay, so this first section will just be an aside. If I have my full talk, if I get through it, you'll see that it's actually very related. But this will be an aside on Q-Ponchhammer symbols. Okay, so a nice combinatorial object, in particular Q-Ponchhammer symbol asymptotics, I should say. Okay, so we should remind you what is a Q-Ponchhammer symbol. So we have, maybe that looks too much like a Q. So this is defined as an infinite product. So 1 minus A, 1 minus QA, and so on and so forth. And as long as I assume that Q is a modulus less than 1, this will define for me a nice analytic function. Okay, so this is a very familiar object. Now, where do these Q-Ponchhammer symbols come up? Well, you've probably seen them in the context of orthogonal polynomials, but there are a variety of other ways that they come up. So for instance, they come up as partition functions for simple combinatorial objects. So if I look at minus QQ infinity, this is going to be the partition function, what are called strict partitions. And I take Q to the size of the partition. So by a partition, lambda I can also associate with a Young diagram. It's just a collection of boxes that are kind of weakly ordered in this way. So this would be lambda, and the size of lambda here would be the sum of the number of boxes, which I guess is 7. Okay. So very simple generating function. Another one, which is slightly more complicated, but not much, is just the inverse of QQ infinity, which is the generating function for all partitions. So both of these rather simple to see, but if you haven't proved these before for yourself, if you get bored during the talk, feel free to prove any of these statements. Just from a probabilistic perspective, these are already nice because it tells you that if you divide the right side by the left side, this defines a probability measure on certain classes of partitions. And you can start to ask about the behavior of these probability measures, the behavior of asymptotics as Q goes to 1, for instance, in which case the partitions get supported on larger and larger sizes. So this is one motivation for studying Q-Ponchhammer symbols. Another one is in the study of Q-deformed special functions. So the simplest, or one of the simplest, is the Q-gamma function. And this actually takes a very elementary form. So there's some simple factor. There's a normalization, which is this QQ infinity. And the only non-elementary term is QZ infinity. Now it's, just staring at this for a moment, it's not at all clear, why this is a deformation of the Q gamma function, but, or of the usual gamma function, but the claim is that as Q goes to 1, this converges to gamma of Z. And the type of convergence is generally, say, on compact interval or compact regions in the complex plane. It gets more subtle when you ask about understanding how, when Z is completely unbounded, how close the two things are. And actually, this turns out to be very important for us. So I want to just tell you one word about the asymptotics of these Q gamma functions as Q goes to 1. So, of course, we know that the usual gamma function, there's all sorts of tail behaviors. There's Stirling's formula. There's, if you move in different regions of the complex plane, you have different asymptotic results. So a very natural question is, what happens when Q is close to 1 but fixed as Z varies in the entire complex plane? And can you prove some sort of results that behave in a uniform manner as Q is going to 1 but Z is unbounded? So let's take Q to be like e to the minus epsilon, just so epsilon will go to 0, and as before, we'll take Z in the complex plane. And now I want to look and tell you about the asymptotics of Q Z Q infinity, which of course is the only non-trivial part of this Q gamma function. So the first thing to observe is that when Q gets very close to 1, the product that we're looking at looks a lot like 1 minus 1, and then products of things that are very close to 0, right? And in fact, you need something on the order of epsilon inverse terms until the powers of Q overwhelms this so that you no longer see something like 1 minus 1. So what you would actually expect is that this will decay exponentially with a rate which is like epsilon inverse. So if I took the logarithm, you would expect that there's some negative constant times epsilon inverse as the first order decay. And it turns out that that constant is zeta of 2. So this already is a remarkable fact. And then on top of that, there are corrections. And there's a correction that's of order log epsilon. So I'm just telling you this. Feel free to try to prove it. And then, you ought to somehow see a gamma function, because I said that the gamma function arises. And you see that in the order 1 asymptotics, where you have gamma of Z divided by 2 pi. Now, I'll say that there are lower order terms, and I'll just write dot, dot, dots. It turns out that these dot, dot, dots are actually the most important thing, especially for our work. And I'll just mention a little bit about them in a moment. But this is the first type of asymptotic that one tries to prove, and actually turns out to be quite important. Now, there's, just for curiosity, and also because it does end up being very useful, if you put a minus sign, now you have lots of terms that take the form 1 plus 1, right? When Q is very close to 1, it's like 1 plus 1. So there's lots of terms that are close to 2. So now you expect exponential growth. And so indeed, there is exponential growth. There's of order epsilon inverse. And the constant ends up being 1/2 of the previous constant, so zeta of 2 over 2. And then you similarly have some corrections, but no longer a gamma function. What was a log epsilon correction becomes log 2, and then lower order terms. And so what turns out to be a very, very important part of the work with Elisa is, can you still hear me? It's a little frozen.
Yeah, we can still
Hello?
hear you. And you're
You
not
can still,
frozen.
okay. I can't see you guys, but anyway, that's okay. So it turns out that very important is to control these uniformly in Z. And I won't go any more into this, but we'll see at the end why such control may in fact be very useful. And it's because we end up taking kind of integrals over Z, unbounded integrals, which involve these types of expressions. Okay, so this was the first part of the talk, an aside on Q Ponchheimer symbols. Hopefully there's a few things for you to absorb here. And if you get bored during the rest of the talk, feel free to just focus on these. In the end of the talk, we'll see the role that these Q Ponchheimers play. Okay, so putting that aside, we come to the main question of the talk, or the main subject of the talk, which is the KPZ equation. And so let me start by just saying, what is the open KPZ equation? So I don't assume that people are that familiar with stochastic PDEs, and I won't really rely on any properties. I'll just basically rely on some intuitive understanding of what it might mean. So, but let me still write it down. Imagine that we have a time parameter t bigger than or equal to 0, and a space parameter x, which is chosen in the unit interval 0, 1. Now I'm going to say that a function htx, which is real valued, solves the open KPZ if it satisfies the following equation. So it's a random evolution, so it's actually going to be a measure on trajectories, but I'll think of, I'll describe what I mean in a moment. So H should satisfy a quadratic Hamilton-Jacobi equation with viscosity. And the only thing that is kind of non-classical is that it is driven by a squiggle that is supposed to denote something called space-time white noise. Now, don't worry if this doesn't make total sense. I'll draw a picture. Picture should help. And then a little later, we'll encounter an object that's a nice, simple, discrete Markov process that's really a discretization of this, and that's the open ASAP, so a more combinatorial object. Now, so the evolution is basically that you have your height function. It evolves through this smoothing given by the Laplacian term. It involves a nonlinear dependence on the boundary, on the slope through the derivative. And then it's constantly being roughened by some sort of noise that's kicking it in independent ways and in space and time. Now, since we're on the unit interval, we need to impose a boundary condition. And what turns out to be physically the most relevant boundary condition is not to pin the height. That is kind of an unusual type of boundary condition, but rather to enforce a certain slope on the derivative. So that the derivative when x equals 0 should take a value, say u, and when x equals 1, it should take another value, say minus v. So pictorially, we should imagine the following. So you have some boundary, so this is say 0 and this is 1. And now we have some interface which starts out, and locally the slope here should be u, and locally the slope here should be minus v. And now I start to run this, and for a given instance of this space-time white noise, I will get an evolution on this, and maybe I'll kind of give you it at a later time. Maybe it looks a little bit, it's changed a little bit over time, and it starts to evolve. Now, the evolution should respect that the boundary derivative should still be u and v, or minus v here. But it will, inside, it will be subject to this KPZ evolution. So the real question for us is to understand what happens when we run this for a long time. Now, before doing that, I just want to point out that there are some subtleties in even making sense of this object. And this has been a subject of a lot of interest over the last decade or so. You see that the space-time white noise is roughening the interface sufficiently that it actually looks locally like a Brownian motion. And so if it looks locally like a Brownian motion, it's not differentiable. And so in particular, taking something like the second derivative is a little suspect, but taking something like the derivative squared is very suspect. And on top of that, looking at the derivative at the boundary condition doesn't really make any sense. So there's work to be done in making sense, rigorous sense of the equation, and it turns out that the correct way to do it is to actually say that h you simply define as log of z, where z solves what's called the stochastic heat equation, where the boundary condition transforms into what's called Robin boundary condition. I won't go into making sense of that, but I just want to make sure that it's clear this is a well-defined object. So the goal of our talk, really one of the goals of studying this equation has been to understand its stationary measure. Now we should be careful in saying, in describing what that means. If you just look at the picture I've drawn, at least from the way I've drawn it, if you run this evolution for a long time, you imagine that actually the height will just kind of drift away. Maybe it will move to infinity, maybe it will just diffuse. So there will be no stationary measure for the height function itself. It's kind of like if you look at a random walk on Z, there's no stationary measure for the random walk itself. So what we need to do is actually look at the height increments. In other words, look at the slope field. But what I really want to say is if I subtract off the value at 0, and I look at what I see moving away from that value, that thing is the thing that should statistically become stationary over time. So the goal is going to be to find, a random function. So it'll depend on u and v. So it'll be some random spatial function. So a function of a single spatial variable. So this dot should be in the value in the interval 0, 1, such that the following. So if I start my KPZ equation off at time 0 with initial data given by, in distribution at least, by this dot, by this HUV, then it should follow that if I look at the height function at time t as a function of its spatial variable, and I subtract off the value at 0, then this will remain equal in distribution to HUV. Okay, so this is the goal of the game. It's to find the stationary measure for the height increments, and this should be true for all t. Okay, so is it clear at least what the goal is? And you have this evolving interface. You want to understand its stationary behavior. Okay, you guys are still there, right? It's still frozen for me, so I can't see any movement.
We are still here. We can still see you. You are not.
Okay, that's what matters. That's what matters. Okay. Okay, so part 3 is to actually solve this problem to satisfy the goal. And this is a theorem between myself and Elisa Kniesel, and posted earlier this year. So the first statement is, well, the statement is, first of all, that there exists such a stationary measure. So part 1 is for each pair UV. So it's not a priori even clear that there exists some stationary measure, right? So the first statement is that stationary measures exist for all choices of boundary condition. So there exists such HUV dot. So such measures. That doesn't tell you anything about what they look like. So let me start to tell you what they look like. So for u plus v equals 0, so the u plus v equals 0 basically means that the slope here and the slope here are, well, that they sum to 0. Well, in fact, that these two, no, not that they sum to 0, that these two things, because here I've drawn minus v to be the slope, that the two things are equal. So if the slopes agree in this u and minus v, then the HUV that we've constructed is actually equal to a Brownian motion in the spatial variable with drift to u equals minus v. So in the case, say that this is going to be equal itself to u, so kind of like what the picture I've drawn, this will converge to an increment process that's just a Brownian motion with a drift. So a very, very simple object. Now, what happens when that's not the case? So for u and v general, well, the first thing is a probabilistic statement, which is that the increments of HUV can be what I'll call stochastically sandwiched. I won't really tell you what that means, but between the increments of HUU and the increments of H minus V, V. I think there should be a HU minus V. So what I'm saying here is that in the case where the two slopes don't agree, I can still compare. If I imagine I've reached my stationary measure and I look at the increment between, you know, a third and 2/3, that increment statistically is dominated above and below by something that looks like a drifted Brownian motion. So already there's some information, some control over what these might look like. Now, the thing that is probably most interesting and certainly most relevant to the audience that I'm talking to right now is the actual description of the stationary measure. So it's not just that we have existence, but we have a very concrete description of it. And I'll give you 3 forms of the description. The first is the one that Elisa and I initially developed. And this involves orthogonal polynomial measures. So, and this applies when U plus V is bigger than 0. So we give a very explicit form in the special case of U plus V equals 0, which is in the physics literature called the fan region of the phase space. So when U plus V is bigger than 0, we can characterize the multi-point Laplace transform of HUV. So is given via a dual process. It's called the continuous, we call the continuous dual Hahn process. Now, I won't write down what that means, but I'll give you an example of a formula that associates it, because, you know, just to give you a sense. So in the special case, when U and V are both positive, things will be simplest. There will be no atoms in the orthogonality measures. And so I'll just write that one down. And we have some parameter zeta, which is going to take values between 0 and 2V. Then I can write down the Laplace transform. So the Laplace transform is the following. So I look at, maybe that's like C not a zeta. I look at my HUV, and it's simplest if I just look at the value at 1. So what this really means is I've run my interface, so going back up to this picture, I've run my interface for a really long time, and now I look at the sort of height difference between where it is at 0 and where it is at 1. So this is going to be in stationarity, my HUV of 1. So the question is, what is its distribution? In the case when U plus V equals 0, the Brownian case, this is just a normal random variable, right? We know that because of the second part of this theorem. But the question is, what in general will be its distribution? And the way that we describe it is in terms of its Laplace transform. And well, it's first given by something that looks like the Laplace transform of a Gaussian. So there is some Gaussian component to it. And then it's written in terms of an integral. Still something kind of like a Gaussian, e to the minus r squared. And then a measure that depends on this squiggle, r dr. And then the same thing where I just put in mu of 0. And I need to tell you what this mu is. And so the mu is the relation to orthogonal polynomials measures, and in particular the continuous dual Hahn measure. And it's given by this sort of ratio of gamma functions like you would often see in that realm. So this one gamma function and another one squared, and in the denominator we have 2ir gamma squared. Okay, so this is a nice measure. It's not a probability measure. It's not normalizable, but nevertheless, this, because of the minus r squared, this integrates to something finite. And this gives us the form of the Laplace transform. In general, if you want the multi-point Laplace transform, it will involve lots of products of this form, where you can actually end up writing the right-hand side in terms of an expectation over a sort of a dual process, another stochastic process, which has transition and marginal distributions of this form, actually related to the orthogonality measure for this continuous dual Hahn polynomials. Okay, so this is the description that we have, and I just want to emphasize, we only have these exact formula descriptions in half of the space. We know the existence everywhere. But this is, maybe well, I haven't given you the full level of formulas, but, there was something a little unfulfilling initially, which was that, we have lots of formulas, but we don't have a probabilistic description for, well, what does this process actually look like? In the special case of u plus v equals 0, we know it's a Brownian motion, and this is a very nice stochastic process. But otherwise, we just had formulas. And so luckily, pretty soon after our work, there were two groups that were able to invert our Laplace transform formula. Okay, and the first group, and I'm not going to write the names out, I'll use the initials, was Brick, Kuznetsov, Wang, and Weslovsky. Okay, and actually they had a little bit of an advantage because we had given them our formulas a few years earlier when we were still working on this. The project took about 3 years. So we had shared some of these formulas with Brick, and so they'd been working on this for some time. And what they showed was that our Laplace transform formulas could be inverted, so that the HUV that we constructed is equal as a process in the x variable. So I'll put x, so as a process in x, to the following. So a Brownian component, I'll just write it as, I'll use a slightly odd notation, whatever. And then the difference of some other process y with its value at 0 and its value at x over 4. Now let me tell you, what are these two things? So first of all, B is just a standard Brownian motion. So by doing this x over 4 and times square root of 2, it's basically a Brownian motion of variance, I guess, 1/2. In the special case, when u plus v equals 0, the y thing ends up also being a Brownian motion with variance 1/2, but with the drift. And that's why you end up with the nice Brownian description. But in general, this B is going to be independent of the y process, and y is given in the following way. So it's given by, so y has what's called a Rado-Nikodym derivative. I'll just describe it in words, against what can be called a free endpoint Brownian motion, actually times square root of 2, but which is given by, is proportional to the following. Okay, so a picture is worth 1,000 words. So, so what is this y process? So I have 0 and 1, and my y can start anywhere. So it's not pinned to starting at a particular height, and it can end anywhere. And so really the starting and the ending points are like, well, the starting point I can take, say, by Lebesgue measure, and the end, and then I just run a Brownian motion away from that. So this is the underlying, not probability, but underlying measure. And then I'm going to reweight that by a penalization, or by a term which is related to the exponential of, now my u's and v's need to come in. So what I have is, I have the value, so this is y. So here's y of 0, here's y of 1. And I penalize, or I reward, based on 2u, the value of y0. Okay, and then I also have a term that involves 2v, the value of y. Now I guess this should be a quarter by the normalization. It just simplifies formulas a little to do that. Of 1/4. Okay, so these are two terms. So let's imagine for concreteness that u and v are both positive. So this really, really wants y to be positive in both the starting and the ending points, right? So there's, in the case of u and v positive, there's a strong push in the upward direction. Now that needs to be compensated by something, and it is. So there's a energy that is encountered as you move across from 0 to a quarter. And this takes the form of actually exponential penalization for being high. So this is the form of the Rado-Nikodym derivative. And what you should understand that is that if y in the middle is high, you exponentially penalize your probability of seeing something like that. So really, there's a very strong force that's trying to push you down in the middle, but there's also a linear force that's trying to lift you up at the boundary. And these balance so that you can actually define a probability measure on these free endpoints. And then what you do is you look at the increment from 0 to a position x/4. And this is one description of the stationary measure. Okay. Now, there's another description which is actually simpler. And I'll tell you in words how the two relate. So there's I don't know how to write. So Barraquand and Ledoux-Salle, also soon after, gave another description, which is that, so it has a similar form initially. So it's a √2 times a Brownian motion at time x/4. And then I'll write a y tilde, some other process. And I don't need to do this centering by the value at 0 because the value at 0 will be pinned to be 0. And so so b is equal to Brownian motion, and it's independent of y, which again has a Rado-Nikodym derivative against a drifted Brownian motion. So in the first picture, I didn't need to put in the drift because I had the u and the v, but now I'm going to say a drifted Brownian motion. So with a drift against drifted, I think √2 times Brownian motion with a drift v. So it needs to involve this v. Maybe it's 2v, I don't remember. And the Rado-Nikodym derivative is proportional to, so Rado-Nikodym against this, which is proportional to the following. So I look at the integral from 0 to a quarter, e to the -2 y tilde of s ds, and that I raise to the power -u minus v. So basically, again, it's some sort of penalization. You know, when y gets too large, this is really penalizing you. Well, I guess it depends on the. So let's see, u plus v is bigger than 0. So there's some balance of terms I need to think for a moment about. Anyway, this is the form that they give. And now we have, you know, two very nice probabilistic descriptions. So let me give a few remarks. How are these different results? So there's 3 different results, 3 different types of results. How are they related to each other? Okay, so the first is how do these two probabilistic formulas relate? And well, the way that you go from this Brick et al. Work to the Barraquand Ledoux-Salle work is actually by integrating out over the starting value of y0. And when you do that, such an integral, you end up you end up basically using the fact, you know, there's this nice classical integral, you know, e to the ax e to the x dx. This is equal to b minus a gamma of a. So you end up getting this type of expression that we're seeing here from this b to the -a term. And so going between these two is basically just amounts to integrating out over the value of y0. So that's not a particularly hard or deep concern. Now, the more interesting connection is to go actually between this type of formula and the type of formula that I showed you up here. And that's actually facilitated, and I'll just say it in words, but that's facilitated by the following. So, you know, this idea of looking at a Brownian motion subject to some exponential potential, some exponential killing, is an object people have studied. And And you can write down a sort of generator for that, a Laplacian minus a multiplicative exponential term. And that's, well, the heat kernel for that is something that's a certain type of Kilbrownian motion. And there's a heat kernel, which is called the Yabukovich heat kernel. And you can write that in terms of, basically in terms of Bessel K functions. And so when you try to compute, say, Laplace transforms here, you end up computing certain integrals involving Bessel functions, Bessel K functions, exponential integrals. And those type of integrals very readily lead you to expressions of this sort of type, where you have products of gamma functions. And so it's not at all, once you have this formula here, it's not so hard to go back to get our formula. The inspiration, of course, is going from our formula to this. And that's why it took some work. It took a few years for them to figure out how to do that. Of course, this brings to the question of, if we have these three different descriptions of the stationary measure, how do we actually show that any one of them is actually stationary? And that's what I'll come to in just a moment. Okay. But for that, I just want to maybe add one more remark, which is that there was a restriction in our result, at least for the exact formulas, that u plus v would be positive. And one can see very clearly that that's important, but maybe not so clearly from this formula. But if you look at this formula of Brick et al., if u and v, say, are both negative, then in that case, actually, the drift will also push you in the downward direction. And there'll be no way of normalizing this to define a probability measure, and you'll really be up in trouble. So on the other hand, after you do this integrating out, you get a formula here of Barquin and Ledoux-Sall, where the sign of u and v is really not so important. And this is a well-defined object for any values of u plus v, or any values of u and v. And so it's reasonable to hope that this is actually going to be the stationary measure for any values of u and v. We don't have a proof of this, but one might hope to be able to show it by some sort of analytic continuation or some argument of that sort. But who knows? The other comment before I go into the how of this is that I've been careful, or hopefully careful, in just saying that we've shown the existence of stationary measures, and I give a description of those stationary measures. We have not yet proved the uniqueness of the stationary measure. I very much expect it will hold true, and there are results, say, in periodic domains where people have proved this, actually stronger versions of this. So I'm pretty sure, I'm happy to conjecture in the paper that these are unique, and so any initial data will converge to this, but that's not something that's been proven yet. Okay, so how do you show that something is the stationary measure for the open KPZ equation? In the usual setting of a finite state Markov chain, you would take the generator, or Markov process, you take the generator and you would take your measure and you would hit the measure with the generator and you'd show you get 0. Okay, so that's one way, where you diagonalize the matrix, you do something of this sort. But here we're dealing in highly infinite dimensional settings where the generator of this process hasn't even been defined. So there's really no clear way in the continuum to go about trying to prove that these are the stationary measures, even if you have formulas for them, even if you have a nice probabilistic description. So what we'll do instead is we'll appeal to a discretization, and the discretization is called the open ASAP. And actually, I'll explain that this is a discretization of open KPZ. Now, if we can give a description, or if we can quantify the stationary measure for open KPZ equation, and we know that this evolution converges to the open KPZ evolution, so open ASAP goes to open KPZ, then its stationary measure should converge to a stationary measure for the KPZ equation, and this gives us a construction. And you see why this doesn't prove uniqueness, because yes, there's a limit point, but maybe there are others that would be accessed in some different way, not through such an approximation. So you need to rule that out. Okay, So let me describe to you an ASAP, and this is a model that's been well studied for 50 years. All sorts of beautiful combinatorics and integrable properties of it, but let me just describe the probabilistic description. So it's a model for stochastic transport, and you'll see through integrating, it's going to be a model for interface. So it will already at the microscopic level, it's kind of related to what I said the KPZ is supposed to model. And the way it will work is the following. I'll have n sites, 1 through n, and then I'll have these two boxes that you think of as reservoirs. Now, these reservoirs can insert particles at a rate alpha into position 1 if there's no particle there. If there is a particle, it can remove it at rate gamma. These are according to exponential clocks, independent. All of them are independent. Now, you remove particles at the boundary at n at rate beta, and you insert particles at rate delta. Inside of the system, you have particles, which I'll draw with dots. And the rules are there that particles jump left and right. So they jump left with a rate q, right with a rate 1. And the only rule is that they can't do jumps which would cause collisions. So a jump where one of these particles moves left, the one on the left moves right, the one on the right moves left, that is suppressed. Okay. So all of these numbers that I've drawn are the rates of exponential random variables that basically determine, when an exponential clock rings, one of these jumps occurs. And it's a Markov process, so it means that all of these are independent, and once a jump has occurred, you kind of can imagine resetting all of these clocks. So hopefully this is a well-defined discrete system. So this is an interface. This is not an interface. This is an interacting particle system, but there's a very simple connection to interface growth, which is through looking at a sort of integration of this. And so what I'll do is I'll draw a little down slope everywhere above an empty site, and above occupied sites, I'll draw an upslope, and I'll just proceed in this manner for me. So this goes up, down, and then finally up. So this defines an interface. And now the jumps that we were just describing induce jumps on the interface. And you want the jumps to be local. So for instance, if a particle gets fed in at rate alpha, that should correspond to taking this interface and moving it down. So that jump, maybe I'll do it in red, it's a downward jump is rate alpha. Of course, if you had the opposite slope, it would go up with rate gamma. And you have a similar picture over here. So you can swap from up to down, and that one is beta, the other direction is delta. And then internally, you also have jumps. So this could end up getting inverted into a max, or this could get inverted into a min. And that jump occurs at rate q, and this one at rate 1. So this defines a dynamic on the height function itself. Okay, so I'm going to define my height process. So I'll keep track of n. N is the system size. It'll be a function of time and x. And the x will take values in the, I guess, the finite set 0 through n. I think that's the way, yeah, so it starts at 0, goes into n. And I can, of course, linearly interpolate in the manner that I've shown. So now the question is, what in the world does this have to do with the KPZ equation that we have been talking about? And well, the answer is that it's a discretization of the KPZ equation. And this has been known in some form since the mid-90s. So Pertini and Giacomin in the mid-90s studied ASEP not on the finite interval, but on the entire line. And what they observed was the following remarkable fact. Actually, they didn't reserve, this was observed in the 80s by Jürgen Gardner, they used it, was that if you look at q to the height function, so the same q of this asymmetry, then on the full line, Gardner basically observed that this q to the height function solves a microscopic version of the stochastic heat equation. So this was on the full line, and then this is the starting point for the analysis of rotating chalk mean, who then show that as Q goes to 1 in a suitable way, this microscopic stochastic heat equation goes to the continuum stochastic heat equation. And so kind of taking logarithms, you get that H in some form converges to the KPZ equation. The fact that this solves a microscopic stochastic heat equation is itself remarkable. And it's a special case of what's called Markov duality, one particle Markov duality, which is actually an algebraic property of the system that is known for ASAP, related to quantum group symmetries. Now, in the open setting, no such thing was known, and the starting point for the work to relate these two was the observation that I made with my then postdoc Hao Shen, which is that there is actually a way of showing that this open ASAP also satisfies a microscopic stochastic heat equation if you restrict the parameters a little bit. And so we enforce something that's called that we call Liggett's condition. This was named after Tom Liggett, who used a similar condition in the 70s when he was studying ergodicity for ASAP on the full line. And this is some relation that we assume that reduces the number of parameters from boundary parameters from 4 to 2. And this is just an assumption that the alpha over 1, so over the right jump, and gamma over Q, so over the left jump, should equal 1. And similarly, we restrict the beta and delta in this manner. Okay, so this actually reduces the space of parameters, but still we have one parameter for each side, which will play the role of setting a sort of local slope to the interface, or a local density of the system. And so under Liggett's condition, then we show that Q to the height function solves a microscopic stochastic heat equation with some version of a discrete Robin boundary condition. Okay, so some relation between the microscopic derivative, the discrete difference operator, and the value of this Q to the height function. Okay, so this is really the starting observation. And then there's some scaling that needs to be involved in order to relate these two models, these two processes. And the first is that we apply what's called weak asymmetry scaling. And that involves taking Q to 1. So actually taking it, so n is going to go to infinity. We're going to imagine taking n to infinity, and then Q will go to 1, like e to the minus 2, n to the minus a half. So n is going to infinity, n to the minus a half is going to 0. So this is really going to 1 in some nice way. Finally, we need to scale our parameters, alpha, beta, or gamma, delta, in a way that they're all converging to being close to a half. So this is what we call triple point, because it corresponds to zooming into a triple point of the phase diagram for this model, something I won't go into. But it involves setting alpha and gamma equal to a half, and then plus in the case of alpha and minus in the case of gamma, something of order n to the minus a half. And this is where the parameter u is going to come in. And there's a similar type of formula for beta delta. I'm not looking at the ratio. I'm just writing it as they're both equal to a half, but then one of them is equal to plus and one of them is minus the over 2 n to the minus a half. So I don't want to harp on these scaling. What I do want to just emphasize is that you have reduced yourself to these two parameters, u and v, and these are really tuning the strength of these boundary reservoirs. And simultaneously, we're applying this weak asymmetry. And then the theorem, which is with myself and Hao Shen, and that was in kind of half of the phase space, and then strengthened by my graduate student, Shalin Parekh, says the following, which is that if I consider a sequence of initial data, so I need to know something about the initial state. So if my initial data satisfies some Brownian-like Holder bounds, I'm being imprecise here. So it doesn't need to look like a random walk, but it needs to have some sort of comparable Holder bounds. Let me not say exactly what this means. then the following will have will at least be tight, but and let's say, well, okay, let me write it down. So we look at the height function at a time scale which is n squared. So t is going to be varying in that scale. And I look at a spatial scale which is, well, like n times x, where x now I take to be in 0 and 1. So I'm taking n to infinity. Now this needs to get rescaled. This is kind of fluctuating on a very large scale now. So I need to rescale it by multiplying by n to the minus a half. And then I need to do some centering that ends up being related to of this form. And then the claim is that this will converge as n goes to infinity as a process in the two variables x and t to the open KPZ equation with these boundary parameters u and v. And this convergence is provided that we have convergence for t equals 0. So in other words, if the initial data converges under this scaling, this diffusive scaling to something, some measure maybe, then so too will the evolution away from that. And that evolution that you converge to will be given by the open KPZ with these parameters u and v as the parameter. Okay. So this is the relation between these two models. And now the question is, how do we actually make use of this to access the stationary measure for the open KPZ? And so that's the final subject, which is how to take asymptotics of the open ASAP stationary measure. Now, open ASAP is a finite state Markov chain, right? There's a finite number of particle configurations, like 2 to the n, and it's irreducible, aperiodic. So there's a unique stationary measure. Okay, so that's not an issue. We know this unique one. The question is, what does it look like? And the stationary measure for the particle process induces a stationary measure on the increments of the height process, because, well, the increments are actually the particle process. So the question is, what does that stationary measure look like, and how can we take its limit? And so there are really two parts to this story. The first is that we want to show what in probability is called tightness. It's really a form of compactness. We want to show tightness and Brownian like Holder bounds. Okay, what do I mean by this? So for a given n, let's say n is 1,000,000, there is a stationary measure for the open ASAP. There just is. And I put in all these scalings. Now, what does it look like? Well, what I want to show is that if I apply these scalings, well, with the t equals 0, so I don't need to worry about that term. If I apply this scaling,
Ivan, sorry to interrupt. You cannot see us, but could you maybe round it up in a few minutes?
Yep.
Thanks.
So so I need to show that this object that I've bracketed here is tight. It's that there's some compactness, that there are some subsequential limits. And that's the first part. And I need to show that it's comparable, that it satisfies really the conditions of the theorem, these Brownian-like Holder bounds. And this is really a probabilistic thing, and it relies on two facts. So one is that for u plus v equals 0, you actually have the stationary measure is product Bernoulli. So that's the case that will correspond to the Brownian motion limit. And then you have some version of the stochastic sandwiching in the spirit of what I was saying. And that these two facts together give you what you need for the tightness in the Brownian Holder bounds. Now, the harder part is identifying the limit. And so let me just tell you very briefly what happens here. So in general, the invariant measure is only known through what's called product matrix or matrix product ansatz. It goes back to the early 90s by Derrida, Evans, Hakim, and Pasquier. Now, that's a complicated ansatz, and you need to find representations for the matrices that arrive there, for the operators. And Uchiyama, Sasumoto, Adati found in the early 2000s representations in terms of Jacobi matrices for Askew-Wilson polynomials. So using that, Brick and Weslowski were able to recast these types of formulas in terms of something they called Askew-Wilson processes. And so the last thing I'll write down, then I'll end, is just an example of what such a formula looks like. So this is for the stationary measure of ASAP with n particles. And if I look at the generating function for the total number of particles, so the taus are zeros or ones. So to look at the total number of particles in the system, that's what the sum is. And this generating function takes a nice form. It's written in terms of some integral. R to the n against a measure, and I'm not going to write down the measure, but then there's a similar integral where where r is equal to 1, or sorry, where s is equal to 1. And this measure, nu s, is related to the Askew-Wilson orthogonality measure. And so just to, there's a whole host of formulas of this sort in terms of all sorts of generating functions in terms of these Askew-Wilson orthogonality measures, the Askew-Wilson processes. And so just to bring this back to the original aside, you see, the Askew-Wilson orthogonality measure involves all sorts of Q-Ponchhammer symbols of the type I started talking about in the beginning. And here we want to take integrals, unbounded integrals against these types of measures. So the asymptotics that end up being relevant, because we're taking Q to 1, are exactly the type of asymptotics I alluded to in the beginning. And you need this control over these uniform asymptotics because you're taking integrals of this, and we need to basically do dominated convergence. So putting all of this story together leads us to our formulas, which leads us through some inversion to these nice descriptions of the invariant measure. Okay, so I hope I've given you some flavor. Obviously, I haven't gone much into the combinatorics, but of the steps and the coherent set of ideas that leads you to this, what I consider a very nice result. And I'm happy to answer any questions at this point. So thank you very much.
Okay, thank you very much for your nice and interesting talk. So are there any questions here in Lumini? So maybe I can ask a quick question. So actually I have two quick questions. So in one of your inverted Laplace transforms, it was kind of obvious that the case u plus v equals 0 does give back the Brownian motion, but in the other one, it's not that obvious. Is there something deep behind this, or is this just my lack of knowledge?
No, so you're completely right. In the one on top, the starred one, it's not at all clear that u plus v equals 0 gives you Brownian motion. The reason is that there's this extra y0, right? So you need to compensate by looking at y0 minus yx over 4, and y0 itself is going to be distributed in some non-trivial way. So it's not clear just looking at this that you have this nice Brownian picture. If you do the integration out, which leads you to the box picture here, then of course it's quite obvious. If you look at the level of our formulas, the case of u plus v equals 0 is also a little bit degenerate. The measure that one gets is you need to do some asymptotics in order to actually show that you recover the Brownian. So from the point of identifying the Brownian measure, by far the third description is the most elegant way to do it. You can do it in each of the other cases, but it takes more work.
And maybe just another question. So essentially, you say you have the continuous dual Hahn polynomials at the level of the KPZ, and then you discretize, so you get Askew-Wilson. So, well, what is the corresponding? What is in this correspondence? What relates to the continuous dual Hahn polynomials in the discretization?
Yeah, so the type of formula, this in particular, this box formula, which is this measure that's related to the orthogonality measure of the continuous dual Hahn polynomials, in the discretization, you end up with the Askew-Wilson polynomial orthogonality measure. And so the dual process that describes, here I've only given you a one-point Laplace transform, but if I want a Laplace transform at positions x1 through xd, I can give you formulas for that, and these are actually written in terms of an expectation of another process, of a stochastic process whose transition probabilities are also written in terms of these continuous dual Hahn polynomials. And in the discretization in the ASAP setting, this is in terms of Askew-Wilson processes as well. Askew-Wilson orthogonal. Yeah. Thanks. These Askew-Wilson processes are very beautiful. They were first identified by Brick and Wisłowski in 2010, and they actually came out of a completely different question, which is the classification of what are called quadratic harnesses. So in probability, a linear harness is something where if you condition on the value at A and B, well, the expectation is a linear function of the two always, but that the variance should be a linear function of the two values here. A quadratic harness has the property that the variance is a general quadratic function of the values at A and B. And so Brownian motion, Poisson point processes, these are simple examples of these, but they gave a characterization of the entire space of processes that have this quadratic harness property, and these are the Askew-Wilson processes.
Okay, thank you. Maybe we should see if there are any questions from online. Sergio, I think, go ahead. Yeah, go ahead.
Well, can you hear me? Hello, this is Sergio. I think I lost my concentration there for a second. I think, well, I'm not entirely sure whether the formulas that you gave after number 4 there are valid for u plus v less than 0. Could you comment on that? And also, in your first formula, what is the difficulty in deriving a description for u plus v less than 0?
Sure. Okay, so the formulas, this one of Brick and et al. Is, one can't normalize. You know, we start out with this free Brownian motion where both endpoints are free. In order to define a probability measure, you need to show that, you know, when you integrate over this Lebesgue measure, you get something finite. And that really requires having u plus v be positive. So this one, the restriction is due to that. However, what I was saying is that once you integrate out over the y0, you get this formula in the box. Now the formula in the box makes sense when u plus v are, when the sum is negative. Now that doesn't mean that that is the invariant measure for KPZ in that case. There's, but it's a plausible guess, and that's something that they actually conjecture in this work. As to the subject of why, you know, why we end up with this u plus v condition, well, in the guts of it comes down to the fact that the Askew-Wilson process formulas that Brick and Wisłowski derived for ASAP involve a similar restriction on parameters. There's a restriction in the case of ASAP to what's called the fan region, which is half of the phase space of boundary conditions. The matrix product concepts exists outside of that, but the reduction to the Askew-Wilson processes requires that as a technical condition. And so from the start, one doesn't have, you know, formulas outside of that regime. Now, you know, again, you can ask, well, what if you try to analytically continue in u and v? And it's a very natural thing, and to try to do that at the level of the formulas. But you also need to prove that the stationary measure is itself analytic in some sense in the boundary parameters u and v. And so that's, you know, that there's not some phase transition that occurs on the line u plus v equals 0. I don't think there will be, but one needs to rule that out and show analyticity and, you know, of suitable quantities.
Thank you. So, well,
thank you.
Oh, yeah, sorry. Okay, I'm done. Thank you.
So, okay. So I don't see any more questions. So I think, in view of the time, I thank Ivan again for his nice talk.